So today is the test review day for limits involving vertical asymptotes and end behavior. So let's take a look right off the bat. I just wanted to go, from the latest lesson to the earliest lesson, because those are the most time consuming. So let's take a look at the limit as x approaches infinity for 9x to the seventh plus 3x squared minus 4 over 6x squared minus 12x. So right off the bat, let me get my pen. We see that we have infinity. If I plug in x equals infinity, I get 9 infinity to the seventh plus 3 infinity squared minus 4. Let's be honest right there. Like that's infinity over infinity. Like that's 9 infinity to the seventh over 6 infinity squared. But what calculus teachers won't tell you in plain old English, because it's not technically true, but there's different kinds of infinity. Infinity to the seventh is different from infinity to the second power. So when in doubt, my good buddy, whenever I'm confused about this indeterminate form in my thought bubble, infinity over infinity, I don't like it. So we can call my good buddy L'Hopital to solve that problem for me. So if I apply L'Hopital to the top and bottom of this problem, so that is going to be the derivative of the top over the derivative of the bottom. So that becomes 63 x to the 6 plus 6x, and the derivative of negative 4 is 0, over, let's take the derivative of 6x squared, that'll be 12x. And then the derivative of negative 12x, well, that's negative 12. Okay, if I plug in infinity here, I still get 63 infinity to the 6th power plus 6 times infinity over 12 times infinity minus 12. Well, that means I still get infinity over infinity, in which case I can still do L'Hopital's rule. L'Hopital to the rescue means I get the limit as x approaches infinity. And now I'm going to still take the derivative of the top. Oh, I'm going to need a calculator for that. So 63 times 6 is 378. So that's 378x to the 5th power. And the derivative of positive 6x is positive 6. And then the derivative of the bottom, 12x, is 12. And the derivative of negative 12 is negative 12. The derivative of negative 12 is 0. So, do I still get infinity over infinity? Well, no. Now, if I plug in infinity, so I get 378 times infinity to the 5th plus 6 over 12. I mean, come on, no contest. That top part of the equation beats positive 12 any day of the week. So what this means is I basically get infinity over 12. Infinity divided by 12 is infinity. So therefore, the limit as x approaches infinity for this rational function is positive infinity. Now, another way you could do this is, what if you know the answer right off the bat? Yeah, I'm totally okay with that, because the other way to look at it is, okay, so I have the limit as x approaches infinity. I know that it's infinity over infinity, but the question is, which is going to win the race, the top or the bottom? So I look at the top. The top is a degree 7 function, and the denominator is a degree 2 function. So I pay attention to the fact that we have a degree 7 over a degree 2. I'm going to put this in quotes. Infinity to the 7th power is greater than infinity squared. Okay? Even though it's not formal calculus lingo, if that makes sense to you, be my guest. Because if the numerator has a higher degree than the polynomial, then the end behavior as x goes to infinity is infinity. Y wants to go to infinity if the numerator beats the denominator in the race. Okay? So, problem number 2. The limit as x approaches infinity for 15x cubed rather, minus 14x squared plus 9x minus 7. Well, let's just be real. If I plug in x equals infinity, I'm going to get infinity over infinity, which is an indeterminate form. So an indeterminate form, infinity over infinity, means that I can always turn to my good buddy L'Hopital to bail me out. So if I apply L'Hopital's rule to this equation, that means I take the derivative of the top and the derivative of the bottom, and hopefully that problem goes away. So the derivative of 15x cubed, that'll be 3 times 15, that's 45x squared. The derivative of negative 14x squared, that's going to be negative 28x. And the derivative of positive 9x is positive 9. And the derivative of negative 7 is 0. Now let's pay attention to the bottom. The derivative of x to the fifth is going to be 5x to the fourth. And the derivative of positive 2 is 0. So I do my plug-in x equals infinity, and what do you know? I get 45 infinity squared minus 28 infinity plus 9, 5 times infinity to the fourth, blah, blah, blah. You and I both know that all we care about are the leading coefficient, the leading degree of the functions. And I care about the star teammates. I care about the LeBron James. I care about the Anthony Davis. I care about the Stephen Curry. I care about the star player of the numerator and the denominator. So it's going to be infinity over infinity. So what does that mean? It's an indeterminate form, so I have to apply L'Hopital's rule to bail me out. So if I apply L'Hopital yet again, the limit as x approaches infinity. So the derivative of the top is going to be 90x minus 28, and the derivative of positive 9 is 0. And now I'm left with 20x to the third. If I plug in x equals infinity, I get still infinity over infinity because I plug in 90 times infinity minus 28 over 20 infinity cubed. Well, my good buddy L'Hopital is going to bail me out one last time. So the derivative of 90x is 90. The derivative of negative 28 is 0. And the derivative of 20x to the third is 60x squared. And now in my thought bubble, if I plug in infinity, I get 90 over 60 times infinity squared. I mean, which one's greater? The one that's 90 or 60 times infinity squared? Sounds like a kindergarten insult. I hate you 60 infinity squared. But the point is, the denominator is beating the numerator. So if we have 90 over 1,000, 90 over 1,000,000, 90 over 1,000,000,000, 90 over 1,000,000,000,000, you can see that this value is getting closer and closer and closer to 0. So therefore, the limit as x approaches infinity is 0. So we've got 90 over infinity, which is 0. So close to 0, it's practically 0. It never actually reaches 0, but you'll get like 0.001 eventually or something like that. The other way you can do this is, what if you don't want to apply L'Hopital's rule? What if you're like, come on, I've seen this, I know how to do this. Well, here's your method. Look at the degrees of the top and the degree of the bottom. So the degree of the top is 3, because the highest exponent is 3. So the top is a degree 3 polynomial. And the bottom is a degree 5 polynomial. I don't care about the others. They're irrelevant because the leading degrees tell the story about the speed of the function, if you will. Who's going to win the race, the top or the bottom? So if you only look at infinity, give it 15. Give it 15 as a teammate. 15 times infinity cubed versus infinity to the fifth power, infinity to the fifth power is going to win. So if the denominator at the end of the behavior, as x approaches infinity, if the denominator beats the numerator at the end, that means that it gets closer and closer to 0. That's only because the denominator wins. All right, problem number 3. The limit as x approaches infinity for 5x squared plus 11x minus 130 over 7x squared minus 200. Okay, if I plug in infinity, I'm going to get 5 times infinity squared plus 11 times infinity minus 130. Let's be real, I only care about the leading degree. 5 times infinity squared over 7 times infinity squared, still I get infinity over infinity. And that's confusing. That's called an indeterminate form. Sorry, I smudged the ink a little bit. But yeah, it's an indeterminate form, and I'm not happy. So I call on my good buddy L'Hopital to bail me out of this situation. So the limit as x approaches infinity, take the derivative of the top and the derivative of the bottom. Well, the derivative of 5x squared is 10x. The derivative of positive 11x is positive 11. And the derivative of negative 130, as big as it may be, is still 0. Take the derivative of the bottom. The derivative of 7x squared is 14x. The derivative of negative 200, as big as the number might be, it's still going to be 0. So now I use my thought bubble. Okay, 10 times infinity plus 11, I mean, come on, that's infinity. Over 14 times infinity, that's infinity, but it's still infinity over infinity, and I'm still confused. That's called an indeterminate form, so I still use L'Hopital's rule. So as the limit as x approaches infinity, where I take the derivative of the top and the derivative of the bottom, the derivative of 10x is 10. And the derivative of 11 is 0. So my top becomes 10. And the denominator, the derivative of 14x is 14. If I plug in x equals infinity, well, I mean, there's no variable. So this flattens out to become 10 over 14. But I think I can simplify this fraction. I'm going to divide the top and bottom by 2, because that's the greatest common factor of 10 and 14. I'm going to divide the top and bottom by 2. And now I get 10 divided by 2 is 5, and 14 divided by 2 is 7. So the limit as x approaches infinity is 5 over 7. And I know what you're saying to yourself. Hey, wait a minute, that looks exactly like the leading coefficients of x squared and x squared, because the degree of the polynomial is 2 and the degree of the polynomial is also 2 on the top and bottom respectively. So it's not a coincidence that the coefficients of the leading variable are where the curve flattens out. So if I re-look at this problem, notice that the degree of the top polynomial is 2. And the degree of the bottom polynomial is 2. Remember that we only care about the leading degree because that tells us everything about the function. If that's the case, then we can pretty much just look at these two, and the curve is going to flatten out at the end behavior by the coefficients, 5/7. We could have just done this the entire time. And that's only because the degree on the top matches the degree of the bottom. One more time. So I'm not going to do L'Hopital's rule a million times, because you might get a problem where it's like x to the 13th on top and x to the 13th on the bottom. You don't want to do L'Hopital's rule that many times. You'd rather just go, okay, what's the big picture? I'm going to get infinity over infinity. There's no question about that. But since they both have the same degree, it's going to flatten out. Degree 4 and degree 4. However, as it flattens out, the only relevant parts of the function are the coefficients of the leading degree. So, in other words, the limit as x approaches infinity for this ridiculous function is 18/30ths. But I want to see if I can simplify this fraction. So 18 and 30 can both be divisible by 2, 3, and 6. So why don't I divide the top and bottom by 6? So now, if I divide the top and bottom by 6, 18 divided by 6 is 3, and 30 divided by 6 is 5. So, just make it look nice. So as x gets closer and closer and closer to infinity, the curve is going to flatten out at 3/5 or 0.6. Once again, it'll never actually reach 3/5. It's the intent behind the end behavior. Hopefully, it'll get arbitrarily closer and closer to 0.6. Okay? So now that we got the end behavior out of the way, since that takes the longest to explain, let's go back to the vertical asymptote kind of problems. So remember, we've got the limit as x approaches -9 of 1 over x plus 9. So we go to our thought bubble, because even though you guys might chuckle, you guys might laugh, thought bubbles got me through calculus. I didn't understand calculus the first time I saw it, the second time I saw it, the third time I saw it, but the fourth time I saw it, I was like, oh, okay. So it comes down to using your brain from the left and the right side. So if I take a look at x equals -9, -9 plus 9 is 1, I get 1 over 0. And in this case, remember, I lost my train of thought. If it's 0 over 0, that creates a hole in the graph usually. If it's infinity over infinity, okay, does the curve go to infinity, 0, or flatten out? But if it's 1 over 0, that means that this is a vertical asymptote. In other words, the graph will be this imaginary line where the graph, one direction will go to infinity and the other will go to negative infinity, or both will go to infinity, or both will go to negative infinity. Those are the 4 outcomes, basically. And I mean, you know what I mean. Like, one will go to infinity, the other one will go to negative infinity, and so on and so forth. So we need to figure out which of the 4 categories of vertical asymptote we're dealing with. So once again, the trick is to think one step to the left and one step to the right. And I don't even mean a full step. I mean a decimal. So we need to take the left-hand limit and the right-hand limit. Let me just get these part out of the way. Sorry about that. So if I take the left-hand limit, so once again, this makes me think just barely to the left of -9. So a number that's, since we're in the negative world, I'm thinking so close to -9 on the left, it's like -9.0001. So let's plug that in. We'll plug in x equals -9 from the left side, but we're thinking to ourselves -9.0001. So we got 1 over the left side of -9. Yes, that's legitimate calculus notation. So if that's the case, I get 1 over, so if I'm thinking -9.0001 plus 9, am I going to get barely positive or barely negative? I'm going to get barely negative. So I call this notation the left-hand side of 0. So if I've got 1 over 0, that is some sort of infinity. But now I'm looking at, okay, so I've got a positive 1 on top, and I've got negative 0.001 on the bottom. So that is a positive divided by negative. Therefore, the left-hand limit is negative infinity. Let's take a look at the right side. So if I want to calculate the right-hand limit, what am I thinking to myself? I'm thinking just barely to the right of negative 9. Sorry about that. Paper's just flying everywhere. If I'm thinking just barely to the right of negative 9, I'm thinking negative 8.9999999. So I'm going to plug in 1 over, sorry about that, the right side of negative 9. If I were to literally plug in negative 8.9999999 plus 9, am I going to get barely positive or barely negative? I'm going to get barely positive. So 1 over the right side of 0. Remember that 1 divided by 0 is some sort of infinity. We've got a positive divided by a positive, so that is a positive. Therefore, the right-hand limit as x approaches negative 9 of 1 over x plus 9 is positive infinity. So if I were to graph this, again, it's not drawn to scale. Remember, we care about this negative 9 part right here. And if I draw this imaginary dotted line, again, I'm not drawing an exact graph, but if the left side wants to go to negative infinity and the right side wants to go to positive infinity, they can't agree on where they want to go as x approaches negative 9. So therefore, the limit does not exist, Lindsay Lohan. That is the answer. If we evaluate the limit, the left-hand limit and the right-hand limit do not exist because the left-hand limit and the right-hand limit do not agree. Okay, let's take a look at number 6. The limit as x approaches negative 16 for 17 over x plus 16 quantity squared. Now let's plug this in. In my thought bubble, if I plug in x equals negative 16, and I get 17 over 0 squared, well, 0 squared is still 0. So 17 over 0, I'm not happy, not because it's a whole, but because it is a vertical asymptote, which makes me work a little bit harder. Because I still need to figure out, well, is the limit going to infinity? Is the limit going to negative infinity? Or is the limit not going to exist? It's one of those three. So I'm going to take the left-hand limit. And then I'm going to take the right-hand limit. Okay. So if I plug in the left-hand limit, remember, this is negative 16.001. So I've got 17 over x plus 16 quantity squared, but I'm going to plug in the left side of negative 16. That is 17 over, remember, we haven't applied the square yet. If negative 16 plus 16 is 0, but I'm thinking just barely to the left of negative 16, is negative 16.001 plus 16 going to be barely positive or barely negative? Barely negative, so that's the left side of 0. But remember, we're going to apply that square. So if I had negative 0.000001, As small as it may be, let's use our logic. What's a negative times a negative? A negative times a negative is a positive. So 0 from the left side, quantity squared, becomes 0 from the right side now. So 17 over 0 from the right side, that's a positive divided by a positive. 17 divided by 0 is infinity. So the left-hand limit is y equals positive infinity. Okay, well now let's do 17 over the, we're applying the right-hand limit now. So now I'm going to apply a number that's just barely to the right of negative 16. If this is like negative 15.9999999, what is negative 15.9999999 plus 16? Is that going to be barely positive or barely negative? Barely positive. So we haven't applied the square yet. So this is the right side of 0, quantity squared. Now, it's small enough as it is, but let's just use common sense. What is a positive squared? Still a positive. So this is 17 over still the right side of 0. And 17 over the right side of 0 is positive infinity. Sorry, the paper just slipped a little bit. So the left-hand limit as x approaches negative 16 is y wants to go to infinity. The right-hand limit as x approaches negative 16, y wants to go to infinity. So therefore, this is going to be one of those graphs. Let's just say I put negative 16 way over here. You can plug it in on Desmos, but I'm just giving you a rough graph of what this looks like. So this imaginary dotted line is where x cannot actually be, but the graph says both the left and the right side go up to the sky. So therefore the limit does exist. The limit as x approaches negative 16 for this vertical asymptote is positive infinity. The left and the right agree. Okay, 2 more and then we'll call it a day. Okay, the limit as x approaches 18 for negative 4 over x minus 18. Okay, well, if I plug in 18 minus 18 in the denominator, I get negative 4 over 0. And I'm not happy about that because that's a vertical asymptote. So I need to apply the left-hand limit and the right-hand limit. This time I'm going to start with the right-hand side. All right, so if I apply the right-hand limit as x approaches 18, I'm going to plug in x equals 18, but I'm going to think to myself a number that's just barely bigger than 18, like 18.001. So if I plug in 18.001, is 18.001 minus 18 going to be barely positive or barely negative? Barely positive. So I got negative 4 over the right side of 0. Now, since I've got negative 4 over 0, that's going to be an infinity. But let's pay attention to the signs that we got. Negative divided by barely positive is still negative. Negative divided by positive is negative. So the right-hand limit, x wants to go to negative infinity. Now, looking at the left-hand limit now, if I want to apply the left side of 18, so let's think 17.9999999. If I plug in 18 from the left side, 17.99999 minus 18, is that barely positive or barely negative? That's going to be barely negative because 17.999 would be negative 0.001. Well, I've got negative 4 over 0, which is going to be some sort of infinity. But a negative divided by a negative is a positive. So therefore, the left-hand limit as x approaches 18 is positive infinity. The right-hand limit as x approaches 18 is negative infinity. So if I were to draw just a rough graph of what's going on, let's just put, we're going to the right side right here. So let's just put 18 over here. I'm going to put this imaginary dotted line. Can't touch this. I don't want to get sued, so I'm not going to sing the song. If x wants to, as x approaches 18 from the left side, it wants to go to positive infinity, so the graph looks a little something like this. As x approaches 18 from the right side, it wants to go to negative infinity, so the graph looks a little something like this. So the left-hand limit goes to infinity, the right-hand limit goes to negative infinity, so Lindsay Lohan, the limit does not exist. Because the left-hand limit and the right-hand limit can't agree on where they want to go. Okay, last one, and then we'll call it a day. The limit as x approaches 20 for negative 13 over x minus 20 quantity squared. So if we plug in x equals 20, I'm not going to be happy because this is negative 13 over 20 minus 20 quantity squared. So that's negative 13 over 0 squared, which is negative 13 over 0. Yet again, we have a non-zero over 0, so that creates a vertical asymptote. I got to use the left side and the right side, the left-hand limit and the right-hand limit. Let's go. So I'm going to plug in the limit as x approaches 20 from the left side, negative 13 over x minus 20 quantity squared. Get ahead of the ball game. Okay, so let's say I plug in the right-hand limit. Well, I'm thinking to myself, something that's barely bigger than 20, so like 20.001. So if I plug in the right side of 20, 20.001 minus 20 is the right side of 0. And remember, we haven't squared it yet. So this is negative 13 over, as small as it may be, 0.00001, quantity squared is going to be still really small, but it's still going to be on the positive side. Calculus is weird, isn't it? Well, negative 13 divided by 0 is some sort of infinity. But remember, we've got negative divided by positive, so that is going to be a negative infinity. Okay, the right-hand limit is negative infinity. And now I'm going to apply the left-hand limit. Again, this is 19.9999999. So if I plug in 19.9999999 minus 20, am I going to get barely positive or barely negative? I get barely negative, but hold on, I forgot to square it. So I still got negative 13 on the top. If I've got negative 0.001 and I'm going to square it, as small as it may be, it is still a negative number. So we still use the rules of algebra. A negative quantity squared, a negative times a negative is a positive. So negative 0.001 becomes positive 0.001. And now, negative 13 divided by 0 is some sort of infinity. But a negative divided by a positive is a negative. So the left-hand limit as x approaches 20 is negative infinity. And the right-hand limit as x approaches 20 is negative infinity. So if I were to draw just a rough version of the graph, let's just put x equals 20 over here. I'm going to draw this imaginary dotted line. So as x approaches 20 from the left and right, the graph would look a little something like this. They both go down to negative infinity, even though they will never actually touch each other. The intent is that both of them go to negative infinity. So therefore, the limit as x approaches 20 for negative 13 over x minus 20 quantity squared is negative infinity. Good luck, and we'll be back to derivatives in the next unit. I also added a bonus video called The Mean Girls Problem, where at the end of the movie, I show you how Lindsay Lohan got the limit does not exist for that problem. The next unit will be on writing the equation of tangent lines. So we're back to derivatives. Good luck. Test is due Friday at 11:59 p.m.